Data Skeptic mini-episodes provide high-level descriptions of key concepts related to data science and skepticism. Today's topic is the Bootstrap.
So Linda, I don't know if you know this, but during the last episode I announced that we won't be talking about the election results for a little while. I want to do stuff on polling, but not just yet.
Well, you're telling me right now, so good to know.
I'm going to sort of break that rule a little bit because I want to talk about polling in general. The more people you get, the better your polls are going to be. You know, if you could poll every single person in the United States, essentially get to n equal all, then you'd have a very nice poll, but that's unrealistic for a lot of reasons. It's a similar story in a lot of data science. You can't always get a big enough sample size.
Can't always get what you want.
Yeah, pretty close. I think that's exactly what those guys meant when they wrote that. The Bootstrap, let's first talk about the technique. It is a technique where you have a data set, right? Let's say you have like 100 sample data points.
Yes.
Put them into a bag, shuffle it all up, pull out, one random element.
Mm-hmm.
Take note of what it was, then put it back in.
You put it back in?
Yeah, you put it back in.
Why? What if you draw it twice?
Well, let's get to it. That's a good question, but let's just talk through the method first, because you will draw it twice. Shake it all up, draw again, until you draw 100 out. How many duplicates do you think you're going to get?
Well, there's 100, then you put it back. The second time, it's 1 out of 100.
Right. As you draw a big enough set, it's almost certain you're going to have some duplicates because there's only one way to draw it uniquely.
Mm-hmm.
And that's very unlikely with a large enough set. So then you have this, let's call it secondary sample, and you could train a model or make a decision based on that. Then you could start from scratch, repeat that whole process, do it again. And in this way, you could make n number of models based on this sample of a sample. Let's not worry just yet about why you would do that. Is it clear the process I'm describing?
Sure.
Okay. Now, at the end of that, you could average out the results of all those models based on all those weird double sample data sets with replacement. And the average of those, often by central limit theorem, is going to get close to the correct answer.
No, why?
Each of them represents a different sort of weighting of your initial data set. So some will lean in one direction and others will lean the other way. Let's say we wanted to estimate the average height of women living in Los Angeles. And you went and surveyed 100 women. Mm-hmm. Now, do you think 100 women adequately represent the entire...
No, there's billions of people here. Or is it millions? It's millions.
Let's just say you took 100 women, surveyed them on their height, and then took the average. How close is that average going to be to the true average?
You surveyed everyone, took the average. That is the average.
No, you surveyed and you got 100 women to participate.
Oh, to the true average?
Yeah.
I guess it would be within 25%.
Yeah, probably something like that. This is why statistics are useful. You can have a small sample and help predict the larger population. As that sample size grows, of course, you have a confidence interval that gets closer. But it could be very easily thrown off, right? How would it get thrown off?
Well, you could be somewhere where there's a lot of tall models hanging out.
Mm-hmm. What about the short models? Where do they hang out?
They don't have any.
There must be some.
No. People don't want short models.
Well, who's going to be in a movie with Tom Cruise? He's quite short.
Oh, they just put him on a box.
Or similarly, you could end up with, a very, maybe the WNBA is in town and some especially tall woman just happens to be in the survey. She's going to skew it, right?
Yeah.
If you did a survey and 10 of your friends did a survey and they all got 100 different women, then can you see how averaging all your surveys would produce a better result?
Maybe.
Yeah, it should.
Know.
But in that case, all of you went out and got 100 different people. What if you all talked to the same 100 people? You would think you'd get the same answer, right?
By just averaging all of them? Yes,
Yeah.
You would. Because everyone surveyed the same 100, right?
Yeah, that's right. So essentially, the Bootstrap is saying that with this method, now there's no guarantee it can work. Sometimes it doesn't work, and we'll talk a little bit more about when and why it wouldn't work. But it's possible you get a better answer without introducing any new data by using this method of resampling from your sample. Here's my best way of thinking why it does work. So it's not guaranteed to work all the time. But if your sample is kind of low fidelity, that it doesn't bring in enough examples to adequately really represent the population, then this resampling means that on each trial, you're going to have a different propensity for picking out certain cases that represent some subpopulation or characteristics of people. In this height example, if you had a couple of especially tall people in there, just having one or two can highly skew your result a little bit on a small data set. But then there are also only, again, two people in that data set. So on some of your trials, you'll sample them and others you won't. So you're kind of like downweighting them implicitly. But the difference is you don't have to decide who to weight. It just comes out naturally in the statistics, and the central limit theorem kind of kicks in. You'll recall we talked a while ago about random forest that does bagging, which is bootstrap aggregation. That's the bootstrap we're talking about here. That's a case of machine learning where you're trying to train a model, and each model gets its data set from this procedure of sampling with replacement.
Yeah, I mean, guess you might as well randomize it again.
So when I first heard about this, I thought like, well, this probably doesn't hurt, but why would it help?
Because random.
Right, but it's the same amount of data as before. You didn't get any new information.
But you're putting them back in and randomizing.
Yeah.
That's different data.
You're right. It gives you a different sample each time, but why should that result in any new information?
Because random.
I'm trying to decide if you really grasp this deeply or not.
It's like distillation. You distill it once, you distill it twice, you're going to get a different result the second distillation.
Yeah, in a way it is, I guess, like distillation, where you heat it up, turn all the liquids into a vapor, and then you try and capture it at the other end. Different things are going to come through. Mm-hmm. Yeah, that's sort of a way of doing it. Oh, and then what do they do, alcohol producers, when they do blending at the end? Why do they do that?
Consistency.
Yeah, so to extend your analogy there, if you're really distilling it, then it's mixed later, so you're getting the mix of all these different things, and you get a better product from its components. So yeah, maybe we should have started with distillation. That kind of has a nice analogous feel, although I don't know that it works mechanically.
Well then, I think we should have a drink to cheers it. So Kyle, why is it called the bootstrap?
The idea of the bootstrap is like if your boot has like one of those straps on the back and you pull it to quickly get it on, rather than trying to wiggle your heel into a shoe. This is a technique by which you could very quickly get something more out of your data.
Did you just make that up?
No, that's basically the real answer, yeah. I didn't say he was a poet, he was a statistician.
I don't know. I just thought of it like, oh, you're just a working person, so you wear boots, so you bootstrap it or something.
All right, we can go with that one too. So, all right, let's see how exactly you got it. Let me think if I can come up with a demo here. Hold on. How about this, Linda? Let's talk about an experiment. You want to determine if men buy more expensive cars than women, or what's the difference between cars typically bought by the genders. Do you think there's a difference?
Yeah, I'm going to say men spend more money on their cars.
Yeah, that's probably right. Almost for sure, right? How much would you guess? What's the dollar amount difference?
It's got to be like between 10 and 20 grand on average.
Yeah, I would bet, right?
Because if you just go up to the next tier, it's just more expensive.
All right. So you could survey 100 women and 100 men, ask them, how much they paid for their current vehicle. You could take the average of the two and subtract them, and you get a nice estimate, right? Out of those 100 people, just 100 random men, how many do you think own like Bugattis and stuff like that?
I don't know. You don't see that many around, so probably 0 out of 100.
Yep. But there's a chance you might randomly sample one of those. Or, that's kind of an extreme car. But even out of 100 people, there's some probability you're going to get one outlier. Somebody that's driving some very expensive fancy sports car that's sort of like in its own class. And there's also a chance you're going to get some guys that are driving hoopties, right? Mm-hmm. If you were going to use the bootstrap, how do you do it?
You just randomize and keep pulling from your bag to see. Put it back and keep pulling.
Put it back. There you go. And when you average all of those, there's no guarantee, because if your model is truly a independent and identically distributed sample of the full population, then the bootstrap would have very little effect. But with some likelihood, the bootstrap might give you a slightly more precise answer. And in fact, it can also give you confidence intervals, because each one of those averages then, the central limit theorem kicks in, and you can say like, all right, well, I got the average of the averages is my prediction, but you also know the standard deviation of all the averages. So now you have a nice little boundary on the estimate you're trying to create. So for me, I think the rule of thumb is I expect the Bootstrap is likely to help me when I don't have a big enough sample data set to sufficiently describe the system. I've just got some set that represents some lower fidelity example of it. Well, anyway, that's the Bootstrap. All right, Linda, well, thanks as always for joining me.
Thank you for teaching me about shoes.
Well, until next time, I want to remind everyone to keep thinking skeptically of and with data. Good night, Linda.
Or shoes. Good night. For more on this episode, visit dataskeptic.com. If you enjoyed the show, please give us a review on iTunes or Stitcher.